For as long as humanity has existed, one of the deepest questions we have asked concerns the possibility that we may not be alone in the universe. The idea that life could exist beyond Earth has fascinated scientists and enthusiasts for decades. However, turning this intuition into a concrete scientific discovery is an extremely complex task. In recent years, thanks to increasingly powerful telescopes, we have been able to study planets hundreds of light years away, analyzing their atmospheres and searching for chemical clues that, on Earth, are associated with life. Interpreting these signals, however, is far from simple, and every potential discovery requires great caution. It is within this context that, recently, an extrasolar planet has attracted the attention of the scientific community and the media around the world. Its name is K2-18b. The reason for such interest is linked to a study conducted by a research group at the University of Cambridge, which analyzed data collected by the James Webb Space Telescope. According to the researchers, these data would represent the strongest evidence obtained so far of possible biological activity outside our solar system. The news quickly spread around the world, generating excitement and high expectations. It truly seemed as if we were facing a sensational discovery. But what should we actually think about this announcement? Now that the initial media attention has partially subsided, it is useful to pause for a moment and look at the situation more calmly. It is important to understand in detail what this study has really shown and, above all, how it has been received by the scientific community as a whole. To better understand this, we must start from a fundamental consideration. Searching for signs of life on a distant planet is one of the most difficult challenges in modern astronomy. It is not a matter of directly identifying living organisms, but of searching for indirect traces, the so-called biosignatures. Biosignatures are molecules or chemical compounds that, on Earth, are produced or influenced by biological activity. A classic example is atmospheric oxygen, which on our planet is generated largely by photosynthesis carried out by plants. Finding a large amount of oxygen in the atmosphere of a distant planet could represent an important clue. However, the problem is understanding how to detect these molecules at such immense distances. We cannot directly reach these extrasolar planets. We must rely on space telescopes and extremely sophisticated observational techniques. One of the most important of these is transit spectroscopy. When a planet passes in front of its star, a small portion of the starlight passes through the planet's atmosphere before reaching us. Some gases absorb specific wavelengths of light, leaving characteristic imprints in the observed spectrum. By analyzing these variations, scientists attempt to identify the molecules present in the atmosphere. Each gas has a kind of spectral fingerprint, similar to a barcode. In theory, this makes it possible to recognize it. In practice, however, things are far more complicated. The data are never perfect. Even extremely advanced instruments like the James Webb produce signals affected by noise. In addition, the signals coming from the atmospheres of rocky planets are often extremely weak. Added to this is the influence of the star itself. Stars do not emit light in a stable and uniform way. They can exhibit spots, flares, and variations in brightness that interfere with observations, making it difficult to distinguish a true atmospheric signal from an artifact. There is also another problem. Different molecules can produce similar spectral signals. This phenomenon, known as spectral degeneracy, makes it difficult to determine with certainty which gas is actually present, especially when the signal is weak. To interpret the observational data, scientists use complex theoretical models, a process known as atmospheric retrieval. These models depend on numerous parameters and initial assumptions that can strongly influence the final result. And this is where one of the most delicate problems comes into play: false positives. Even if a molecule is associated with life on Earth, this does not mean that it must necessarily be produced by living organisms on another planet. Chemical processes, volcanism, or other physical mechanisms can generate the same molecules in the absence of life. Before seriously claiming a biological discovery, all these alternative explanations must be ruled out. With this general framework in mind, we can now return to the specific case of K2-18b. K2-18b is a planet slightly larger than Earth, belonging to the category of sub-Neptunes. It orbits a red dwarf star and lies within the so-called habitable zone, a region where temperatures could allow the presence of liquid water. Some models suggest that K2-18b may possess a thick, hydrogen-rich atmosphere, beneath which an ocean of liquid water could exist. The first observations by the James Webb had already detected the presence of methane and carbon dioxide in its atmosphere. In those data, a very faint signal also emerged, attributable to a molecule called dimethyl sulfide, or DMS. On Earth, DMS is produced mainly by marine organisms and is considered a possible biosignature. However, the signal initially observed was extremely weak and not sufficient to claim a discovery. The new study analyzed additional observations carried out with the James Webb's MIRI instrument, which operates in the mid-infrared. This region of the spectrum is particularly important because it contains some of the strongest spectral lines of DMS and of a similar molecule, dimethyl disulfide. According to the Cambridge team, the new data, analyzed using two independent methods, would be consistent with the presence of DMS, or dimethyl disulfide. However, distinguishing with certainty between the two molecules remains extremely difficult. The statistical significance of the result is about 3 sigma. This is an interesting value, but it is not sufficient to speak of a definitive discovery. In scientific practice, a solid confirmation generally requires a level of 5 sigma. Moreover, the amount of DMS required to explain the observed signal would be much higher than that produced on Earth. This would imply an extremely intense biological activity, a hypothesis that raises further questions. Independent analyses published afterward highlighted several critical issues. Other chemically plausible gases could produce similar signals, and the significance of DMS depends strongly on the assumptions built into the atmospheric models. In some cases, the observed signal could even be compatible with the absence of any detectable molecule. In other words, if the signal exists, it lies at the limit of the capabilities of current instruments. So what is the situation today? We have new data and more intriguing hints than in the past, but not definitive proof. The interpretation remains complex and the subject of debate within the scientific community. The case of K2-18b shows us how difficult the search for extraterrestrial life truly is. It is not a sudden discovery, but a long and gradual process that requires time, better data, and great caution. Further observations will be needed. More planetary transits, more refined atmospheric models, and laboratory studies to truly understand these molecules. Every step, even those that scale back sensational announcements, helps build a more solid understanding of reality. The road is long, but this is exactly how science works.